All right. Hello. Today we're going to go over the first half of chapter 17. We are in the last unit for the course, which is Organic Chemistry Part 2, which predominantly deals with reactions and mechanisms. And so chapter 17 is going to be all about alcohol. So it's all going to be about this specific functional group, alcohol. And so we actually already did begin to work with alcohols last chapter because we did nucleophilic substitutions where the product would end up becoming an alcohol. And so now we're going to see what alcohols can do. And so the learning objectives, and this is going to be for the first part of the lesson, is to recall the chemistry of alcohols, exemplified by ethanol in the following reactions: combustion, substitution, and in the reaction with sodium. Now, combustion reactions you should already be well aware of. That is the reaction of hydrocarbons, in this case alcohols, so a little bit more than a hydrocarbon, with oxygen, and that your products, if it was a complete combustion, would be carbon dioxide and water, and if it was an incomplete combustion, it would be carbon monoxide and water. And so the other type is substitution to give halogen alkanes, which should seem confusing because we literally just did substitution to give alcohol. So this time we would start with an alcohol and we would end with a halogen alkane. So how can we get the reaction to go backwards is basically what we'll be addressing today. And then finally, we're going to go over the reaction of alcohols with pure sodium metal in its standard state. So let's go ahead and get to it. Once again, chapter 16, 17, and 18 predominantly deal with, it's kind of like a bunch of recipes. It's a cookbook, a bunch of recipes, and how can we turn this functional group into this other functional group, what manner, what method, to make organic compounds, different types of organic compounds. So beforehand, quick bell work. In many countries, plastic waste is collected separately and sorted. Some of it's incinerated. Why is PVC removed from any waste that is incinerated? And so I'm going to, once again, you have the opportunity to answer, and then I will show the correct answer. So if you'll recall, PVC is a polymer, this specific polymer that you do actually you need to know, you need to memorize it, and it does make HCl gas, so its combustion products are harmful. Because it is an addition polymer, it is definitely not easily biodegradable. It does burn easily, so that doesn't make sense, and it is not a chlorofluorocarbon, so it does not contribute to destroying the ozone layer. Alright, so intro to alcohols. Alcohols have a general formula, which you do not need to memorize the general formula, but you do need to know that when you see OH, you are definitely working with that functional group. So alcohols can either be primary, secondary, or tertiary. Just like halogen alkanes, it's really exactly the same. Primary is when you have a carbon attached to one other carbon. The carbon that has the alcohol specifically being attached to one other carbon. When you have a secondary, it means the carbon that's attached to the alcohol is attached to two other carbons, and then in a tertiary alcohol you have a carbon attached to three other carbons. So those are the different types of alcohols you can have. And remember, primary, secondary, and tertiary is actually extremely important to be aware of, just because, especially with the mechanisms we just did, SN1 versus SN2 reactions completely are determined by whether you have a primary or a tertiary halogen alkane. Alcohols have a higher boiling point than expected when compared with other organic molecules that have extremely similar molar masses. So why would alcohols, and let's just throw one up there, C2H5OH versus C2H5Cl, why would alcohol have a significantly higher boiling point? Let's see if you got it. hydrogen bonding, or a stronger intermolecular force. Then the stronger intermolecular force would be hydrogen bonding, and this means that it will require more energy for the molecule to reach a boiling point to change from the phase of liquid to the phase of gas. So then this, remember, checkups are from the textbook, and some of these checkbooks are really good, checkup exercises are really good review questions. So you can be asked how hydrogen bonds arise. And so when they ask how hydrogen bonds arise, they actually want you to draw out the molecules with the dipoles. So draw out molecules with dipoles. And then to show the hydrogen bond connection. Because a hydrogen bond is an intermolecular force, you need to have a minimum of 2 molecules. Because inter, remember, means between, not within. So ethanol molecules. You need to write out 2 ethanol molecules, and then you want to orient them in such a way where the hydrogen bond can take place. So I'm going to write condensed except for the O and the H. Because really where the functional group is this is the only part that matters, because there's no hydrogen bonding going on with hydrocarbons. If you have a hard time understanding the way that I drew it here, I will just draw on the bottom. This is also C2H5OH. But hopefully you can see the difference between displayed, structural, molecular form. So I need to draw 2. Here's what I would do. I would draw the second ethanol molecule backwards. Like literally flip it. Start with the H, then do the oxygen, then do the C2H5. And so you need to include the dipoles. So this would be partially negative, partially positive, partially negative, partially positive. And then you need to at least show 1 hydrogen bond. So you could show either here or you could show there. And the dotted line between the 2 molecules, that is the hydrogen bond itself. Depending on how the question is asked, you may need to, and they probably wouldn't do it with ethanol, but they would do it with water. They may ask you to write the correct bond shapes. And so in order to do that, you would actually have to angle your hydrogens down. To show the correct shapes. So this might be another way you would have to write your answer. All right, so the next question is ethanol mixes with water in all proportions, but hexane 1-ol is less miscible with water. So then why is this? If you remember correctly, from pre-ACE chemistry, miscible was one of those terms that we needed to know when we first covered solutions. And miscible is another word for mixable. Miscible is mixable. So they say that ethanol mixes with water really well, and hexane 1-ol doesn't mix with water so well. And they want you to point out why this could be true. And so when we're answering any of these types of questions, we want to look at the structure of the molecule. And so ethanol is this, ethanol, and hexane 1-ol, 2, 3, 4, 5, 6, is this. And so take a moment and look at the molecular structures and think about why hexane 1-ol would be less mixable. So when we're looking at solubility, we're looking at the idea of like dissolves like, meaning that polar dissolves in polar, nonpolar dissolves in nonpolar. So we'll be looking at the polarity of the molecules. If you look at ethanol, this is the polar section, and then this part right here is all nonpolar. If you look at hexanol, this is the polar section, because you've got that electronegative group, but look at how large your nonpolar section is. So it turns out that the more carbons on the molecule per electronegative group, the less it will dissolve in water. So the more carbons I add, the less it'll dissolve in water. It actually becomes insoluble above 5 carbons, actually. So we would say that hexane-1-ol is not mixable with water. It starts to become insoluble with water as if it was oil in water. Because hexane-1-ol is clear, it wouldn't be really that easy to see, except for the difference in viscosity, which is how thick the mixture is. All right, reactions of the alcohols. So there's going to be a total of 5 you need to know. So I highly suggest that you either are printing out these notes and writing them down, or you are writing in your own notebook and you are rehearsing them with flashcards, because you do need to note all of the different types of organic reactions that we are going over in this unit, and you need to know them by heart. And what I'm going to do in class sessions is we will just do practice reactions over and over and over again, basically to drill it in. All right, so the first reaction is one we've been covering since pre-ACE, combustion. Anytime I have CHO, I can have combustion. It's easy to tell. Just react with oxygen. You make carbon dioxide and water if it's complete. Assume that the reaction is complete unless otherwise noted. So then write a balanced equation for the complete combustion of propan-1-ol and butan-1-ol. For propan-1-ol, it's up to you how you want to do it. You could first draw out the molecule. Propan-1-ol, CC, COH, H, 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 H. So you count the carbons, C3. Count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. And count the oxygens, 1. And then you have oxygen that you're reacting it with. So you have your alcohol. I collapsed all of the hydrogens. I could have written as C3H7OH and it'd be the same thing. It doesn't matter. You can do it either way. I just thought it would be easier to look at the 8 hydrogens together. And then you make CO2 and water. And so then you would have to balance the equation. And so you have 3 carbons, you have 4 waters, and you have, let's see, with oxygen. You have 6 plus 4 on the product side. 6 plus 4 is 10. 10 minus 1 is 9, so this would need to be 4.5. And then for butan-1-ol, you can go ahead and do that one on your own. All right, reaction number 2. Substitution to form a halogen alkane. And so if I have an alcohol and I have any hydrogen halide, which are actually strong acids, as long as I have that alcohol heated under reflux, then I will end up with a halogen alkane and water. Now, what is heated under reflux? Let's see if you can watch. We're going to move to a short video to explain what that is. So.
Welcome to a brief introduction to the technique of refluxing. Now, before we begin discussing exactly how refluxing works, let's consider the problem that it can help us solve. And that is that organic syntheses often require the heating of solutions for long periods of time. Some specific examples of this would be achieving complete dissolution of a stubborn solute, favoring the thermodynamic product in a reaction with multiple pathways, and also increasing reaction rates so that equilibria are reached more rapidly. So all three of these situations beg the question, how can we boil a liquid indefinitely without boiling the liquid away, without losing significant volume? And the answer is we use a technique known as refluxing, which involves recollecting condensed solvent vapor in the same boiling flask from which it originated. Now, before we talk about the technique of refluxing itself, let's take a look at the alternative and why it is we need to reflux in the first place.
Now, the simplest way to heat an organic solution is using a water bath or oil bath and a suspended beaker or flask.
Now, let's take a look at this beaker and see what would happen if we attempted to heat a solution for an extended period of time. Within our beaker, we're going to place two different kinds of molecules. Those of volatile solvent, shown in blue, and those of the non-volatile solute, shown in brown. As we apply heat to this mixture, we expect the volatile solvent to boil. So let's do that now and watch what happens to the solvent vapor as it is formed. In this system, as you can see, the solvent vapor is escaping and not returning to the flask. This means that over time, we expect all of our solvent to become vapor and ultimately escape, leaving behind simply a residue of the non-volatile solute. This is extremely undesirable in many ways. We can heat our non-volatile solute and damage it, and of course, when it's out of solution, it's no longer able to react in the way that we hope that it will. So we need to come up with a technique which will allow us to prevent this loss of solvent as it vaporizes. One solution to this particular problem is to use a reflux condenser. The apparatus depicted in this slide shows, as usual, a lab jack with adequate clearance holding a stir plate underneath of a thermal well. So when the lab jack is lowered, the heat source will be removed. The remainder of this apparatus consists of a boiling flask, which is clamped in place since it's the lowest piece of glassware, and a reflux condenser, which is also usually secured with a second clamp, though it's not shown in this demonstration. Another key feature of this apparatus is that the top of the reflux condenser is open to the atmosphere. This is to prevent pressurizing when we heat the system. To close the top by placing a thermometer, adapter, or stopper or other device into it would be to invite an explosion or a flash boiling event which would cause a great deal of potential damage and possibly injury. Now that we've reviewed the apparatus, let's take a look at what's going on inside of the actual boiling flask and reflux condenser. Just as before, we're going to charge our flask with a volatile solvent and a non-volatile solute. At this point, we're going to use our reflux condenser as a region of cooling, which will...
So basically, before moving on, the idea of heating under reflux is you have to heat this up in order to get the reaction to work, to occur. But the problem is that most of your solvents here are volatile, meaning they will turn into a gas at a low temperature. So the condenser is used to turn that gas right back into a liquid to go back into the mixture.
Our sample to recondense and fall back into the boiling flask. To do this, we attach a water hose and turn on cold water flowing through the outer jacket. The effect that this will have as we heat the boiling flask is to recondense vapor, sending it back to its original location. Let's take a look at this as it happens. I apply heat to the flask, and my solvent begins to boil. But rather than escaping to the atmosphere, when it reaches the cooling jacket, it condenses and falls back into the boiling flask. Therefore, the net change in volume of my solvent should be zero.
Using this technique,
or an
you can
equilibrium.
boil organic solutions
Or an equilibrium is established
extremely long periods of time, for hours and sometimes even days, without significant loss of volume. And this is the benefit of the refluxing technique.
So notice that it said that this could take hours, this could take days for these actual reactions to happen. So if you were to actually become an organic chemist or a pharmacist, the reactions that you would do would take a significant period of time in order to attach the functional group that you would need. All right, so general reaction, alcohol plus a hydrogen halide is a halogen alkane plus water. You need either one of these strong acids, and you do need to have a good high concentration of strong acid, because if you just have a small amount, the reaction won't happen. You'll need a high concentration of strong acid in order for this reaction to occur. Notice it is also alcohol heated under reflux, so you would have to include that in conditions. And by the way, in your Cambridge questions, you can be asked for conditions. So make sure you are writing them down for each type of reaction. That is the main reaction, but there are other reagents that can do the substitution. So basically you could have C2H5OH plus SOCl2, and that will add for you C2H5Cl, and you don't have to memorize the other product or products that are there. However, I will show you here. These would be the other products for SOCl2. What's important to note is this part, and the other is just to get the balancing. What we need to note is chlorine is swapped in for the OH. So you can use SOCl2 for this. You can use PCl5 for this. You can use PI3 for this, and you'll get the halogen specified. It would make sense that, you know, this is going to give you chlorine. PCl5 is going to give you chlorine on your halogen. That'll be your halogen alkane, and this one will be iodine. So then if I had C3H7OH plus PI3, what would be my major organic product? And you don't need to write the others. So it would be C3H7H7, and then it would be just I. If I have C2H5OH plus SOCl2, I would end up with C2H5Cl. If I have C2H5OH plus HCl, and it's in alcohol and it's heated under reflux, I will make C2H5Cl plus water, which again, you don't have to write the other product. So then one more, this time you write the answer, C2H5OH plus PCl5. What do you think the major organic product is? All right. So the reaction number 3 is a quick one. It is the reaction of an alcohol with sodium metal. So if I have CH3, CH2, CH2OH, and I have sodium, pure metal. This is actually a classic reaction. This is a single replacement reaction because you simply have a compound and you have an element. And so sodium will replace what in this reaction? It would replace the hydrogen. So they swap out. And so H, remember, has a positive charge, and oxygen would have a negative charge. And so what you would end up with is CH3, CH2, CH2, ONA, O minus and A plus. And then you would also end up with another product, which you are responsible for knowing this product. When hydrogen gets kicked out, an element gets kicked out, it gets kicked out in its standard state. And its standard state is H2 gas. So that is something that you need to know. Also, it is important to note the little note that I wrote here. The larger your hydrocarbon is, the less vigorous the reaction. So the slower the reaction, the less dangerous the reaction. The less amount of carbons, the faster, the more vigorous it will be. All right, so chapter 17, part 2. There are 4 parts to this chapter, so today I'm going over the first half pretty much, and then next time when we meet, we'll go over the second half. So chapter 17, part 2, esterification and dehydration. So esterification means make an ester, and dehydration means remove water. So esterification, make an ester, and dehydration means remove water. All right, and so these are really going to be reactions 4 and 5. So let's take a look at the actual learning objectives. Recall the chemistry of alcohols exemplified by ethanol in the following reactions: dehydration to alkenes, and the formation of esters by esterification with carboxylic acids, and then to describe the acid and base hydrolysis of esters, meaning that this reaction in hydrolysis can happen either in strong acid or it could also happen in strong base. And actually there are a few key differences, and I'll probably touch base on that on Friday. All right, so first, what is the esterification reaction? First of all, means make an ester. If you'll recall, ester is COOC. Ester is a kook. And what you need to make an ester, your ingredients are, you need to have an alcohol and you need to have a carboxylic acid. So you really need to have your functional groups memorized. If you forgot, you need to go ahead and re-memorize your functional groups ASAP. Actually, on that note, I think I'll post another quizzes on that just to make sure we're on the same page on functional groups. So you need an alcohol, you need a carboxylic acid, and you make an ester and a water. And the idea is that you are removing water, and this carbon and this oxygen now connect to each other. And so this shows the new bond that's being formed. And then you have water as your other product. And yes, you do need to know your other product in this case. So these are your conditions. You need to know your conditions. And so it's a carboxylic acid and an alcohol. And it's either a strong acid catalyst or a strong base catalyst. Typically NaOH, but oftentimes you'll see in questions they might use KOH as well. Remember, your strong bases from last unit are all group 1A and group 2A hydroxides, except for the top 2 in group 2. So how do we name an ester? Remember, there's the ill part and there's the O8 part. The ill part is connected to the single bonded oxygen, and the O8 part is the amount of carbons connected to the double bonded oxygen. So you have to cut the molecule where you see the C double bond O and the C single bond O, and then you name from there. So this right here is 1 carbon, so it's methyl, because it's connected to the single bonded oxygen, and then because this is the double bonded oxygen, it's the O8, and because it's 1, 2, 3, 4 carbons, it is butanoate. There's actually a little trick here. First part of the name, the ill part, is with the alcohol. Your original alcohol becomes the ill, and your carboxylic acid becomes the O8. So if you can quickly identify your alcohol and your acid in a multiple choice question, you could actually come up with your answer really quick. For example, if they tell you what is the name of the ester when you mix ethanol and propanoic acid, it's as easy as saying, okay, this changes to ill and the acid changes to anoate. So it's ethyl to noate. Yeah. We'll take a look at some questions like that so that you see some. Write the structural formula and name the ester. Okay, so a little bit of practice here. Butan 1-ol and ethanoic acid. So it said to write the structural formula. This means that they want you to write it in this manner specifically. So be careful that if you were asked displayed, structural, or skeletal, you do have to write it in that manner or you are not awarded the mark. So butan 1-ol. Remember, you're showing mastery of those early skills as we are going over new standards. Butan 1-ol. CH3, CH2, 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 OH. Ethanoic acid, which I'm going to write backwards. HOCOCH3. 2 carbons, and then this is the carboxylic acid. This is a carboxylic acid, right? And then this is an alcohol. And so what part do I take away to make an ester? If you forgot, let's take a look. You take away the OH from the carboxylic acid, and you take away just the hydrogen from the alcohol. So that is something to make note of. You're taking away the OH from carboxylic acid, and you're taking away just the H from the alcohol. And so what you end up making is CH3, CH2, CH2, CH2O, CO, CH3, where this oxygen here is connecting directly to this carbon. That is the oxygen here connecting directly to the same carbon. What is the name? Well, butyl ethanoate. Butyl ethanoate. I'll ask you, name this ester. This time, you go ahead and name the ester. I'm going to go ahead and write the structural formula just so you have it, and then we'll see if you're right. So ethanol plus hexanoic acid, CH3, CH2, 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 1, 2, 3, 4, 5, 6, hexanoic acid. So it's this way. It's 1, 2, 3, 4, 5, 6, this, and then it's the ethanol, which is OCH2, CH3, sorry. The idea is that the oic acid, I wrote it backwards, but it would be the same thing. This is the hexanoic acid part. You have to have your C double bond O for the carboxylic acid, and then for the alcohol part, you would have the single bond oxygen with the carbon. The name is ethyl hexanoate. And it doesn't matter which order you write. You could write the carboxylic acid first or the alcohol first, or you could write the alcohol first and the carboxylic acid first, whatever's easier for you. Okay, so hydrolysis of esters. Hydro means water, and lysis means break apart. So hydrolysis means break apart. Break apart an ester. The exact opposite of what you had just seen, which was esterification. So these two, the final two reactions are pretty much inverse of each other. There's putting together an ester, and then there's breaking apart an ester. And then to break apart an ester, you either use a strong acid or you use a strong base. So esters are hydrolyzed by heating under reflux with either strong acid or strong base. And let me go ahead and correct that. That's where I should have put that it was a base here. When I'm doing esterification, we can just memorize that it's H2SO4. For that, you don't have to memorize all the strong bases. But for this process of hydrolysis, you would have to write either a strong acid or a strong base. All right, so then when we use the acid and reverse the preparation of the ester, return it to an alcohol and a carboxylic acid, you will have some reactants and some products, but you'll get a better yield of product if you use NaOH. Meaning, if I really want to break it apart, use sodium hydroxide. This is the method, this is my answer if I have an acid as my catalyst. If I have a base in my catalyst, it'll actually be a little bit of a different answer. So let's take a look at a question, practice Cambridge question. The ester CH3, CH2, CH2, CO2, CH3 is responsible for the aroma of apples. When this ester is hydrolyzed by acid in the stomach, what is the empirical formula of the organic acid produced? So they want the empirical formula, not the molecular formula. So let's take a look through the question. I'm going to go ahead and solve this one through for you. I'm not going to make you answer it. I'm going to solve it through, and then you can see if you got it right. So pause the video if you want to see if you can get it right on your own, but I am going to go ahead and just solve this one and not ask you to solve it. So let's take a look. So I have CH3, CH2, CH2, COO, CH3. And I want to hydrolyze it, meaning I want to break it apart. So where do I break it apart? Right here. Break it apart right there, right? And so they're asking for the acid. This is the acid side. So then I need to return the acid and the alcohol parts to what they would normally be. So this would be CH3, CH2, CH2, CO, and then this would be OH. This would be the molecule for the acid. Now let's count the carbons, the hydrogens, and the oxygens to see if the molecular formula is the same as the empirical formula. There are 1, 2, 3, 4 carbons here, C4. There are 1, 3, 5, 8 hydrogens, and there are 2 oxygens. So C4H8O2 is the molecular formula. But the empirical formula is the simplest version of this. So I would need to divide everything by 2. So the answer here is C2, H4O1, or C. Finally, dehydration. Alcohols can undergo elimination reactions which eliminate water and forms a double bond. So dehydration means removal of water. We actually saw this in chapter 16. We saw dehydration was a form of elimination. So dehydration is simply a form of elimination. So I'm going to remove the OH, and I'm going to remove the H, and I'm going to get the alkene. The conditions would be the same as they always are for elimination. So I would be looking for alcohol, and I would be looking for high temperature. Alcohol being the solvent, so alcohol dissolved in alcohol, and high temperature. Which isomer of C6H13OH gives the greatest number of different alkenes when it is dehydrated? I'm going to let you think about this one, and then I'll go ahead and solve it. All right, so this question is asking, how many different molecules could I form if I do an elimination? So this includes both major product and minor product. And so if you take a look at A, this OH goes, and the hydrogen has to go from the carbon next door. Well, there's only one carbon next door, so there's only one choice for the alkene that will be made, and it's right there. So I'm pretty sure one choice is probably not the answer. Let's take a look at B. We have OH, and we can either remove this hydrogen, or we could remove, not that one, that's on the same carbon, or we could remove this hydrogen, one from the neighboring two carbons. So we have two choices of the alkene that could be made. Let's take a look at C. We could take away the hydrogen here. We could take away the hydrogen here. But because this molecule is symmetrical, taking away the hydrogen here would be the same as taking away the hydrogen here. So that would also be two choices. Let's take a look at D. I take away the OH. I take away the hydrogen here. Literally only one choice. We have a dilemma. We have two options right now that give us two choices, but only one of these options is correct. Let's look a little bit deeper. Let's look at our two choices for B and our two choices for C. So I'm going to go ahead and write both out. For B, I would have CH3, CH2, CH double bond, CH, CH2, CH3. And then my other option would be on the other side, CH3, CH2, CH2, CH, remove the hydrogen on the right side, and then CH3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I think I'm missing 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. One more. And that will give me the one on the other side. 1, 2, 3, 4, 5, 6. Okay. So those are my two options for B. My two options for C are CH3, CH double bond C, CH3, CH2, CH3. And the other one would be CH3, CH2, C double bond, CH2, CH2, CH3. Okay. Can you spot the difference between these two choices and these two choices? You're probably not going to like the answer, but here it is. Both of your options in B have a cis-trans variant. Whereas only one of your answers here in C have a cis-trans variant. So this actually is two more choices and two more choices. So in each of these you have two. So you actually have 4 different alkenes when we include the stereoisomers here. Whereas here we don't have cis-trans right here. There's no cis-trans because there's 2 hydrogens on the carbon on this side of the double bond. And if I were to expand that, 2 hydrogens cannot swap places with each other. So therefore no cis-trans isomer. Whoops. No cis-trans isomer would be there. Let's see. That was almost the last question. So the idea would be that there is no cis trans here because this is CH2, but there is 2 cis trans options in B. So this is actually 4 options, and this was 3 options. So when it asks greatest number of different alkenes, we do need to include stereo isomers. All right, so we're almost done. Dehydration conditions, you do need to be aware that the reaction would take place with alcohol vapor and aluminum 2 oxide. Alcohol vapor and aluminum 2 oxide would be your catalyst, and you do need to know this these conditions. And that's it for today. So I am going to be available on Friday to do practice questions and answer questions and go over some more. And I am going to post the quizzes as well. Have a great day.